Yeah, thanks for being here. I'm Florian. I present joint work with Mark Nübel, who was a master student, and with Josef Deichmann, who is my PhD supervisor. And I'm speaking about path-dependent neural jump ODEs and their application to limit order books. So let me start with the problem setting, which is a relatively general setting. So we look at some cat-like RD-valued stochastic process X, and of this process, we assume to have a training set of n independent realizations, xti1 up to xt and j, where the observation times are randomly sampled in a time interval, and also the number of observations can be random. So for each realization of this process, it can be a different number of observations. And you see, for example, here in this picture, the blue path would be the underlying process, so one path of it, and the blue dots is what we actually observe. And additionally, since we are in a multidimensional context, we can also have an observation mask, which tells us which of the coordinates are observed at an observation time. Here in this one-dimensional picture, this is obviously not needed. And then the goal is to learn to optimally predict given the information that we have at the current time, where optimality is meant in an L2 sense, and the solution to this problem is well known. It's just a conditional expectation. However, computing this, if you don't know anything about the underlying distribution, is arbitrarily difficult. So here we see what the goal would be. So the conditional expectation would be the green line. So for example, let me see if this works. Yeah, perfect. If we had time 0.6, we would have the information of all the blue dots before, and we would like to use this information to make the best prediction of the process in the future. And this we want to do continuously in time. So we want to, here it's again. So we want to predict. And then as soon as we get new information, we want to also consider this new information and update our predictions, and this introduces a jump. So we have a jump in the information, which introduces a jump in our prediction. So how do we want to do this with this path-dependent neural jump ODE? So we use two parts. The one is a neural ODE. This drives a latent variable h between any observations. So this gives you a continuous in time evolution of this latent variable through basically an ODE, which is driven by a neural network f theta, which can be trained, and then gives you the evolution of this latent variable. And whenever you have an observation, which happens at a random time, we use an RNN cell which updates this latent variable. So you get the latent variable just before observing the new observation plus the new observation as input, and this gives you the latent variable afterwards. This is just a combined framework, how you could write it, and then we prove theoretical guarantees for this model, which basically say that we converge to the L2 optimal prediction. So as a limit result, we really replicate the best prediction, so the true conditional expectation. So in one example here, this is the picture you saw before. You see that our model really manages to replicate the true conditional expectation basically perfectly. And then one of the examples that we have is to apply this to limit order book data. And in particular here, this is data from crypto exchanges, so Bitcoin and Ethereum. And we considered here two problems. The first was the regression task. So given the last 100 ticks of the limit order book, we wanted to predict the mid-price 10 ticks ahead. Here we compared two relatively simple models, so linear regression and random forest models trained on different subsets of the features, and also just using the last observation. And we see often the last observation is actually better than any of the easy machine learning models. But we see that our model outperforms them always. So being able to extract some additional information. And the second task, which is the more common maybe in the literature, is the classification task. So you categorize your data 10 ticks ahead in up movement, down movement, or staying constant. So 3 classes you want to predict. And here we compared to the back then best benchmark model, which was deep LOB. And we see that also here our model performs at least as good or outperforms this benchmark model. Well, this is the reference for the paper, where there's obviously the theoretical results and additional other experimental results. And I'm happy to take any questions you might have.
So we have time for maybe 3 or 4 questions. Start over there.
So my question is, why would you be sharing this model if it actually does so well and above average on Bitcoin? You just wouldn't share it.
I mean, I'm a researcher, first of all. I don't know, I mean, I did not try to implement this to, make a trading strategy. So I don't know whether this would really give you alpha where you can make profit with it. Okay. So I did not try this out. So this is just some data set. It was also a relatively small data set. So it was trained only on, so the one Bitcoin data set was only 1 day of data, and the others are data sets that are available on Kaggle. It was just, as I said, one application of the model. But yeah, maybe you can try it and.
I took a picture of your paper.
So let me know if you make a lot of money with it.
So the benchmark models you compare it to, so the graph you had up with the mean squared errors, for example,
Yeah.
seems to suggest that some of the existing models that are in the literature come fairly close. Yours is optimal, right? It's provable optimal, but some of these come pretty close, right? The deep LOB comes pretty close. So how would you characterize that? Because the mean squared errors are very
So there's 2 different. So the first thing, this is just the MSE. Yeah. There we didn't compare to the deep LOB because this was really just the classification model.
Okay, yeah.
The others are, so there this was or I didn't find better benchmarks at that time, even though maybe your model that you talked about might be a good benchmark.
Well,
but
even the last observation does pretty good, right?
Yeah, no, it really does. And as you will know, I guess there is really a lot of noise in there, right? So, and this is also what you see. You fit the linear regression model. The funny thing is, for example, you fit it on all the data or on all the features, and then you go down and use less and less features. And the best performing linear regression model is always the one which uses only the last tick and only the mid price of it. So really, as soon as you give a bit more in it, you overfit automatically, basically. And the funny thing is that, our model is huge in some sense. So a lot of parameters, a lot to train and to fit. And still it manages not to overfit. And I think this is the cool thing about it. So you really see you train it, and it doesn't overfit, but instead really manages to do better than the other models. So I think it's about 0.5% if you compute it, but consistently over all those 3 data sets. So it really seems to do better without any overfitting to this huge noise that there is in the data.
And can you talk a little bit about the training of the model? What's the computational expense of fitting the ODE and then also the RNN?
Yeah, also as Patrick said before, it depends obviously on your framework that you use. I would say on this relatively small data set, which is 1 day of this Bitcoin and LOB, takes you maybe a couple of hours to train it. So for sure, much, much longer than all of the competitors. So linear regression and random forest, they're super fast, obviously. Yeah, so I mean, it's a complex model, of course. But you really seem to understand a bit more of the truth behind the data, it seems. And to the thing that you said before, I mean, so our theoretical result obviously is a limit result. So you know, if you increase your training set and if you increase your neural networks that you have behind, then in the limit you replicate the best prediction. But of course, what we see here is finite number of neurons and finite training set. So you don't know whether it's really optimal. You just know that with this method, you're trying to do the best that you can in some sense.
Thank you very much.
This-
That's great. Yeah, we need to move on.
Maybe later.
Stop again.
Thanks.